This video is the start of probability distributions. A random variable is a quantity whose value depends on the outcome of a probability experiment. Random variables are represented by capital letters. Discrete random variables have a finite or a countable number of possible values. Continuous random variables can take on any value in some interval. Now our notation here, we have the P for probability and the brackets a capital X equals lowercase x. And what that means is if X is the number of sixes obtained when a dice is rolled 3 times, then the probability of X equals X represents the probability that the number of sixes is X, where X can take the values of 0, 1, 2, 3. Now I've got that idea here in a tree diagram, and you can see how that links there. So if we've got our possible values of 0, 1, 2, 3, we can use a tree diagram to help find the probability of each of those. But as you can imagine, this tree diagram gets big and messy, especially if we're doing it by hand, which is why this notation is really helpful for us. And then when we start doing binomials in more detail, then you can see how that once again makes this process simpler. So you got this example here, we've got a tree diagram. We can put these probabilities into the table, as you can see here. So our X, which is our top row of the table, is our possible outcome, so 0, 1, 2, and 3. And then the bottom one is the probability of each of those happening. And they're straight from the tree diagram. So for 0, sixes, you would go down the not 6 path, and there's your solution. For 1, 6, we look at all possibilities of 1, 6, which would be down this one. So we have that path. And we also have that path. And then our solution here is those two added together, and so on from there with the other two. Remember, our probabilities still have to add up to 1 as well, just as in a normal probability situation. 2 important facts, just mentioned the second one of these, but the first one is also remembering our probabilities have to be between 0 and 1. Then the second one's just telling us that they have to add up to 1. Example, the random variable X has a probability distribution as shown in this table. Find the value of C. So with C, we know all our probabilities have to equal to 1 when we add them together, so we can use that to find out what C is. Because we then know that 7C plus 5C plus 4C plus 3C plus C must equal 1. They add up to 20C equals 1, so C equals 1 on 20. Then we want to find the probability of X is greater than or equal to 4. Because it's greater than or equal to 4, it means we need to look at when X is 4 and when X is 5, so the last two columns. So the probability of X being greater than or equal to 4, we could say is the probability of X being equal to 4 plus the probability of X being equal to 5, which would be 3 times 1 on 20 for C, and then plus C, which is 1 on 20. And if you work that out, you get 4 on 20, which is equal to 1/5. Now the mean or expected value of a random variable is the average value that we should expect for X over many trials of the experiment. We have this formula here where expected value is the sum of all the X multiplied by the probability. Now just a note here, if our expected value equals 0, that indicates a fair game, and X represents the gain of a player. Now here, what is the expected value of X in this situation? Using that rule there, all we do is we multiply the X by its probability. So we'll have 0 multiplied by 125 on 216 plus 1 multiplied by 25 on 72 plus 2 times 5 on 72 plus 3 times 1 on 216. Put that into your calculator and you'll find the expected value is 1/2. Now remember, as this is a mean or an average, it doesn't have to equal one of our X values, just as a mean of a set of data can be a decimal. That is the same here with our expected value as well. Now we're going to go into binomial distributions as well here because it links nicely to what we've just done. So in a binomial distribution, it describes the behaviour of a discrete variable if the following conditions apply. So we have a fixed number of trials. Each trial has only 2 possible outcomes, success or failure. The probability of success is constant, and the trials are all independent of each other. Any binomial we can represent in this notation: x, the squiggly line, b, bracket n and p. Remember, n is our number of trials, p is the probability of success. If x is binomially distributed, then the probability of obtaining our successes is, and then we have these two formulas here. They're the same, they're just written slightly differently, and you'll see here it links to binomial expansion. So the probability of when x equals r, that the formula for that is our combination of nr multiplied by p to the power of r multiplied by 1 minus p to the power of n minus r. And our 1 minus p can sometimes be represented as q, but that basically is our failure probability. P is success, 1 minus p or q is the failure. But with this, generally, we do just use our calculators, especially if you're doing the IB program at an SL level. So example 1, x is binomially distributed with 6 trials and a probability of success equal to 1/5. What is the probability of exactly 4 successes? So if we're going to use a formula, first of all, we'll write in our notation. So we have 6 trials and our probability of success is 1/5. Now we're wanting exactly 4, so we want the probability of when x equals 4. If we use our formula, that would be 6/4 multiplied by the probability of success, which is 1/5, to the power of how many successes, which is 4. Then the probability of failure would then be 4/5, and that would be 2, to the power of 2, because there'd be 2 failures. Put that into your calculator and you'll get 0.0154, rounded to 3 significant figures. Now I'm going to go to the TI Inspire calculator and I'm going to show you how you can do this with its binomial calculator function. So on your calculator, to do this, you just need to go into a normal calculator page. Then in our menu, we go to probability, number 5, probability distributions, and then for this one, just a basic binomials, putting values in, binomial PDF. In here we'll put our number of trials, so for this example it was 6. Our probability of success, 1/5, or you could put in 0.2, it doesn't matter. X value, it says optional, but for us that will be how many successes we are after, which is 4. Click OK, and there you see our answer is 0.01536 or 0.0154 to 3 significant figures. Our next part of this question is at least 1 success. Now a way to think of this is that it will be when x is greater than or equal to 1. So you could do where you have the probability of x equals 1 plus the probability of x equals 2, all the way up to a probability of x equals 6 with our 6 trials. But sometimes we can make that simpler. In this case we can, because probability of x greater than or equals 1 just means it can't be the probability of x equals 0, which means it will be 1, which is our total probability, minus the probability of when x equals 0. And then we can just use our formula, so it'll be 1 minus 60 multiplied by 1/5 to the power of 0 multiplied by 4/5 to the power of 6, and that gives us a solution of 0.738. Once again, you can do that really simply in the calculator, just like I showed you before. Example 2, on any morning, the probability that Sam takes a bus to work is 0.4. Find the probability that in a working week of 5 days, Sam takes the bus to work twice. So for here, we've got our notation, so it's a binomial again. We have five trials because it's over 5 days. Our probability of success is 0.4. And we want when Sam takes the bus to work twice is what we are wanting, which will be the probability when x equals 2. If you're going to use your formula, it will be 2 multiplied by 0.4 to the power of 2 multiplied by 0.6 to the power of 3. Or just put it in your calculator and you'll get 0.346. Example 3, a drug is known to have an 8% success rate. A medical testing program administered this drug to 2 groups of 10 patients. Find the probability that all 10 patients were occurred in both groups. So we can do this two ways. The first way would be when we can look at each group separately. So we're going to have 10 trials and the probability of success is 0.8. And then we're looking at when the probability of x equals 10. Put that in your calculator and you'll find that equals 0.10737. And then to find that for 20 patients for the two groups, we can just square that answer, which will give us 0.115. The other way you can do it is, in this situation, you can just say when the probability of x equals 20, and then we would be looking at a binomial of 20 and 0.8, and you will find you get the same answer. Now, in the last example, a box contains a large number of carnations, of which 1/4 are red, the rest are white. Carnations are picked at random. How many flowers must be picked so that the probability that there is at least one red is greater than 0.95? Do this by hand first, which is a process, but then I will also show you how you could do this on your calculator. So in this situation, we don't know how many trials, and that's what we're trying to find out. And then our probability of success is 0.25. We know that the probability of when x is greater than or equal to 1 is greater than 0.95, which means 1 minus the probability of x equal to 0 is greater than 0.95. Then from here we can use our formula and solve with information that we know. So when we put it into the equation for the probability section, this is what we'll get. We'll get the 1 minus, and then this is our notation. This is our information put into the binomial for x equals 0. Now in this, it is good to note that this part here, the combination of n0, is equal to 1. So anything where you've got your 0 at the bottom of this notation always equals 1, because it's the first value from our Pascal's triangle in each row, which makes this really easy. And then 1/4 to the power of 0 also equals 1, which means we end up with here 1 minus 3/4 to the power of n is greater than 0.95. Now from here you could put that into n-solve if you've got that function on a calculator, or you can work it out by parts of it by hand. Then it ends up using logs. Here then this will be 0.05 is greater than 3/4 to the power of n. Then from here we can use logs to rearrange different ways you can do it. I'm just going to do it this way, so it'll be the log of, I'm just going to put 0.75 in there rather than 3/4 because it's easier, of 0.05 is going to be then less than n. And then we have 10.4 is less than n, therefore n has to be 11. Now I'm going to show you how you can do this on your calculator. For this example, we have to do things slightly differently as we've done previously. We actually need to store the function. So we need to type in F1 to tell us what we're going in brackets x, and then we want the control and the button here next to the 9. That's telling us that we're going to store something. And what we're storing is 1 minus our situation with the distributions. That would be menu, probability, distributions, binomial PDF. Number of trials is what we're trying to find, so that's x. Probability of success is 0.25 or 1/4, and we want 0 successes. That then stores that as a function for us. We can then show this in a table. So if you just go Control Doc, this brings up a new page for us. Go to Lists and Spreadsheets. Now we want to change this to a table. So if we just select Control T, change it to a table, and then this F1 here is what we just stored our formula in before. Click that and it brings up a table. Now we are wanting when this is greater than 0.95. So all you have to do is go down, find the first time it's bigger than 0.95, which you see here is at 11. So our n would equal 11, which is what we found out by hand. Expectation and variance with binomials. If we have a binomial a binomial distribution, the expectation of x is just n multiplied by p, so the number of trials multiplied by the probability of success. The variance is npq, with q being the probability of failure, so 1 minus p. First example, a biased dice is thrown 30 times and the number of sixes seen is 8. The dice is then thrown a further 12 times. Find the expected number of sixes. With this, it means our x, a binomial, we're going to have the further 12 times, so it'll be 12. Now our probability we need to work out. We currently have previously seen that out of 30 throws, the number of sixes is 8, so our probability will be 8 out of 30. Then we can put that into our notation. And then from there we can work out our expected number. So the expected number is just n times p, so 12 times 8 over 30, which gives us 3.2. And that's it. One more example. A biased dice is thrown 50 times and the number of sixes seen is 12. If the dice is thrown a further 12 times, find probability of 6 will occur exactly twice, the expected number of sixes, and then the variance. So the probability of 6 will occur exactly twice. First of all, our notation, so our binomial, we know the number of trials is going to be 12, and then our probability will be 12 out of 50 from what we've previously seen. The probability that x will equal 2. Put that into your calculator, which will equal 0.244. Then b, the expected number of sixes. So e to the x will be 12 times 12 over 50, which is 2.88. And then part C, the variance. So the variance is npq. So the number of trials, which is 12, the probability of success, which is 12 over 50, probability of failure, which is 1 minus 12 over 50, which will be 38 over 50. And that will give you an answer of 2.19. And that is expectation of variance.